Alright, I want to show you all this part here in this. I've already showed a little of this here in one of my recent videos talking about quantum physics and how to learn some about quantum physics. So when I got to this part the other night, I wanted to come back and film this and show it to you. So I'm gonna show you a little bit here, and then I'll go back in and show you just a little bit more. Where this Sean Carroll, he's explaining this.
One of the things that is hopefully clear by now about the many worlds interpretation of quantum mechanics is that the underlying formalism, the basic rules that give rise to this theory, is lean and mean. It's not an extravagant mess. All we posit to start are that quantum states represent reality fully, exactly, and that such quantum states always evolve according to the Schrödinger equation. That's all they ever do. No special collapses or anything like that. Everything else about quantum mechanics and the world, including ideas that we have, like measurement and collapse of the wave function, is supposed to be derived from those bare bones. If the idea works, it's an amazing triumph of unification and simplicity. Nevertheless, not everyone agrees that the theory is on the right track. Shocking, I know. Other people get worried that they can't literally see or touch the other worlds, and more generally, that the theory stretches our imaginations to the breaking point. So it's tough.
Okay, so this is what I'm talking about here, what he just said. And then I'm going to show you, I'm going to go on in a little bit further, and then I'll go to the part 2 where he's talking about this more.
In this lecture and confront these worries to see what we can say about them. But as we'll see, some worries are more worrying than others. That doesn't mean they're not there, but some worries are kind of pretty easily dealt with. Others you have to think about more carefully. So the next 2 lectures we're going to devote to some of the biggest worries that people have. First, whether the theory is falsifiable and therefore scientific, and then the second, how to recover the Born rule for probabilities. Remember that Everett's original thesis title was Quantum Mechanics Without Probability. Where does the probability come from? So spoiler alert, I think that worries about the falsifiability of many worlds are very much overblown. I don't think that's a real worry for Everettian quantum mechanics. But I think that the worries about the origin of probability are quite respectable. I think there are answers, as we'll see, but we have to think about it very, very carefully. Meanwhile, here in this lecture, we're going to discuss some of the other worries. These are worries that you will often hear repeated, but honestly, I'm trying to be as candid and as fair as possible. These worries are pretty straightforward to answer. They're worries that occur naturally to very reasonable people, so they shouldn't be immediately dismissed. But I claim that once you really understand what the theory is saying, these worries evaporate. So let's go through them one by one.
Okay, so real quick here too, before I get any further. So I'm using this for educational purposes. And this is things that I've been learning and that I wanted to get out here to everybody else and let people understand what's going on with quantum physics. Just some basic knowledge about it. So that's basically all this is here. I'm just sharing a little bit more knowledge here. Alright, so this is just for educational purposes that I'm putting this on here. And this show here is just about to leave Amazon. It's on Amazon Prime right now. This is a 1-season show, and it's about to leave Amazon within the next day. But it's been really interesting and learning.
The most direct objection to many worlds is that it violates Occam's razor. Occam's razor is the principle that says we should look for the simplest effective explanation for any set of phenomena. Or more specifically, in the exact words of William of Ockham, the medieval scholastic philosopher, entities should not be multiplied beyond necessity. We should favor the theory that involves the fewest entities. This was Occam's way of saying, look for the simplest explanation. Now, superficially, that does not sound like the many worlds interpretation of quantum mechanics. In many worlds, there are a huge, maybe an infinite number of actual universes, right? That sounds like a lot of entities. How in the world can you say that this is picked out by Occam's razor? Well, not to be too nitpicky, it really does depend on what you mean by an entity. And this is in a very clear philosophical sense. Just think about, for example, the whole numbers. Okay, forget about quantum mechanics for a second. Think about the mathematical idea of the whole numbers, the set of numbers 0, 1, 2, 3, dot, 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 right? We've all come across this set. And guess what? It's infinitely big. There are an infinite number of elements in the whole numbers, an infinite number of whole numbers. But nobody thinks that the idea of the whole numbers is complicated. It's not forbiddingly complex. As a concept, the whole numbers are very simple. You start with a number labeled 0, and you construct the next number by adding 1. And then you construct the next number after that by adding 1 again, and you repeat. You get all of the whole numbers. This is literally how advanced mathematicians construct the set of the whole numbers. And that set is considered simple because it's not the number of elements in the set that matters. What matters is the number of ideas. The whole numbers are simple as a concept because there's a simple rule that generates them. You start with 0, you add 1, and then you repeat. We could say the same thing about other constructions that have many, many elements, but a simple rule for generating them. The number pi, 3.14159, etc., that contains an infinite number of digits. But the idea of pi is very simple. It is the ratio of a circle's circumference to its diameter. So that counts as a simple idea, as a not complicated construction. There's a simple algorithm, if you like, for making the thing that we're thinking about. And that's how we measure simplicity. The same thing goes for many worlds. Yes, it's true. There are many worlds. It's right there in the name. But as we've said, we don't construct the theory by positing or postulating the existence of many worlds. All we posit are wave functions and the Schrodinger equation. And just...
So also, as you see here, he does show a lot of the equations, and he does go through a lot of the math equations in this throughout the show. But that's not why I'm showing this. I'm not showing you this. I'm showing you this because I just want you to get the basic understanding of quantum physics. And that's basically what I've been doing, is getting the basic understanding of quantum physics. I'm not a math guy, and I don't do all the equations and the math and stuff. So, you know, I'm not a quantum physicist myself either. I'm just learning and getting the basic ideas.
Those ingredients are part of anybody's version of quantum mechanics. There isn't any viable approach that doesn't posit wave functions or vectors in Hilbert space.
Also, watching this is giving me some ideas,
the Schrodinger equation or something.
some things I want to research.
There are some approaches that deny that the wave function represents reality, but that's a different issue for right now. For realists, you think that there are wave functions and they live in Hilbert space and they evolve according to the Schrodinger equation. The thing is that once you've made those assumptions, the worlds are there. You get the worlds for free. If you believe that a single electron or a set of qubits can be in a superposition, which you have to believe in quantum mechanics, then you should believe that the whole universe can really be in a superposition. It's intuitively challenging, but the equations are completely unambiguous. If an electron can be, the universe can be. It doesn't cost any more weight. It's not something you're lifting up with your hands. Many worlds is extremely simple where it counts in the number of ideas underlying the formalism. Quantum state, Schrodinger equation, just those two ideas. Now you might say, okay, but since I can't see those extra worlds, I might as well assume they're not there. That would be simpler, right?
Okay, so this is the main part I want to show you here. So let me back that up just a second. Okay, so this is the main thing I'm wanting to get to here. And I'm going to let it play now and let you hear this part. So this this way you hear it from him. This Sean Carroll from this university.
Say, okay, but since I can't see those extra worlds, I might as well assume they're not there. That would be simpler, right? No, not right. That is not actually fair. You personally might not care about whether the other worlds are there or not. What you care about is entirely up to you. I cannot give you any instructions there. But you can't have a theory that predicts they are there, which quantum mechanics does, and then simply declare that you assume they are not. If you really don't like the other worlds, you have a responsibility. You have to do the work of developing an alternative theory in which the dynamics of the wave function doesn't bring the other worlds to life, as the ordinary Schrödinger equation definitely does. And you're welcome to do that. That's completely fine. Knock yourself out. But then you have to admit that you're building a legitimately different theory. And when you go down the road of building a new theory, you always have to be careful that you haven't secretly made an experimental prediction that will end up ruling out your new idea. People have built these theories, and they can be tested by experiments, so you can't just say, I don't care, there are other worlds. You have to really think about what it would mean for them not to be there. The second worry I want to talk about.
Alright, so that's the main thing I wanted to get at right there. Is there's a lot of people that don't believe that any of this is true. But it's right there in quantum physics, quantum mechanics, that there are other worlds, that we can't see them. And people cannot just say, well, that's not true, I can't see it. I can't see it, I can't feel it, I can't touch it. It's not really there. It is there because of quantum mechanics. And it's something that was forced upon them when they actually did the quantum physics and quantum mechanics. It's not something that they just came up with and decided one day, oh, I'm just going to go ahead and say this is here. They actually did the mathematics and figured it out. So you can't just, people can't just say, well, this isn't true. I can't see it, it's not really there. And you would actually have to do your own theory and your own paper on it and your experiments on it and prove that it's not real. And then they have tests that they can do to prove if you're right or wrong. So that's the main thing I was wanting to get out there.
Okay, time asymmetry. This is a more technical part, right?
Alright, so I'm not going to show the rest of this video, I just wanted to show that part.
Everett, there seems to be.
And this is from Sean Carroll. He's at a university, and he's on this show talking about quantum mechanics. Alright, so that's the main thing I wanted to show. So I wanted to kind of keep this kind of short here, but I wanted to show that people cannot just say, well, that's not true. There's no worlds like that. I can't see them. They're there. Quantum mechanics says they're there. And you would have to do a theory and tests and experiments and prove that they're not there.